Okay, maybe calling it Call of Duty is a little bit of a stretch. It is lacking in certain respects, particularly the art department. But what you're seeing is an attempt to create something that implements the same kind of network architecture that a modern multiplayer FPS game would use. That is, several clients communicating via a central server, where those clients could be potentially very far away from each other, meaning high latency and varying network conditions, but it still feels instant. It still feels like you're just playing on LAN. So that's what you're seeing. Every player here is an individual client, and the game is being ran on a central server. And then all that information about where everything is, what's the state of the game, that's all sent back to every client. So that's where the complexity is, and that's what we're going to go into. What's involved with this. Um, but let's just get the rest of the demo out of the way because there's no way I can actually talk about it in any depth while playing. Pew, pew, pew. Okay, so core to a game is the game loop, which has the general form of while a game is running, poll user input, update the game state, and then render, and that loop will run at 60 times a second for 60 FPS. Making it multiplayer means splitting that up such that the update occurs on a server and clients send their inputs to the server and then periodically get back snapshots of the game state, where everyone is, what shots are in flight in this case. Why don't clients just say that they're at position X, to the server? Well, it's because it would be easy to cheat, right? So sending inputs to the server means the server then runs the game and is the authority on the state of the game. So that would be it if we were just playing, on LAN, where there are effectively no latency or bandwidth constraints. The clients would just send their inputs and then, every frame get back a snapshot of the game state and blindly rendering it. But when the clients and server aren't literally wired together, it will take some time, for the inputs to get to the server, and then to get back the snapshots. So here, when I move left or right, you see the camera tilts instantly. Now that's just a visual effect for when I press the key, but there is some time from when the camera tilts to when I'm actually moving, and so I'm simulating some latency on my machine. But even with a little bit, it still actually gets pretty unbearable. So that's what we would have to live with if all we did was send our inputs back to the server and then wait for the snapshots back to actually drive the rendering. So that's one problem. Now, the other issue is that games typically render at 60 FPS. So in order to blindly render the last frame given to us by the server, we would need to have the guarantee that we would get a snapshot every frame and that those snapshots would be in order, which is feasible on LAN but just not over the internet. So those are the two main issues. Waiting for snapshots back to actually drive our experience means that we would have to live with a significant amount of lag. And due to sort of fundamental network constraints, we will have less snapshots than back than the frame rate that we would want to render at. So those are the two main issues. So let's walk through the client and server code. So the server has a time that it is continually incrementing, and that is a sort of source of truth for when and where things are happening. And pretty much every message that is sent between them has a timestamp attached to it. So when a client first connects to a server, the server will send with that message the timestamp for the client to then know, okay, this is what the server's time is. It will the client will increment that time along with it, and then occasionally those things will be synced up. So then every frame, the client will send its input that is registered to the server. And along with that, it will send, the time that this input was registered and an incrementing sequence number. The server, when it actually registers this input, it will sort of buffer it, and then every so often it will do a sort of simulation tick, which it will then take the inputs that it has for that player, and it will apply the input. It will apply the physics, and then that will sort of modify the sort of model of that player that the server is keeping. And then after a few ticks, it will send a snapshot of where everyone is. So it has that model of all the players, and from that it will build this snapshot, and then it will broadcast it to all the different players. And with so each snapshot is the players and the shots that are in flight, and for each player it has the last processed sequence number, so the last processed input that it has used to actually simulate the game. And so the significance of this is that when in order to do sort of client side prediction, we don't just send the inputs to the server, but we send them and then we store them, and then we immediately apply them. And so you'll notice that not there, but the apply input and apply physics functions are the same between the client and server. This is ran for all the players, but this is just ran for the client, this particular client. So we buffer, we sort of store the inputs as we send them off, and then we immediately apply them. And then when they come back, when a snapshot comes back from the server, process snapshot, when a snapshot comes back, we say, okay, this is where the server says that we are, and this is the last input that it has processed. Now we have kept the last, however many inputs. They say the last, 60 inputs, and each input has that sequence number, and so it's processed up to input 30. So, but we have like input 50 inputs, right? So we have 0 through 50 inputs, but it's only processed up to 30. So what you do is you say, okay, well, here is where we are as per what the server is saying, but then reapply the preceding 20 inputs that we have buffered, or however many we have buffered, reapply them, and then that's where we are now. And then that will just go and run and run and run and run, right? So that incrementing sequence number is just that source of truth of, okay, here is what the server has processed, and based on that, here's where the server says we are. And then because we've stored the inputs after that haven't been received by the server, or have been received but we haven't received a snapshot back, keep them, reapply them, and hopefully the player will be in the same position that they were before the snapshot came in. Now they might be in a slightly different position because maybe a packet was lost and the server didn't process it, so it's like, okay, well actually you're in a bit a bit of a different position. But under normal circumstances, they should be in the same position as they were before the snapshot came in. And so it's very important that we actually share the same sort of functions to update the game state. So that's why we have the shared apply input, apply physics functions. Now, because these snapshots are less frequent than the frame rate of the game, we can't just render the latest one. So every snapshot has attached to it a timestamp. And because the clients know the service time, what we can do is we can store the last sort of n snapshots and then look to render a snapshot sometime in the past by interpolating between two. So if we go to update render time, what we can do is we can sort of assess the quality of the network connection dynamically by looking at the newest snapshot time relative to the client's view of the server time, and asking pretty much how much future do we actually have buffered. If we consistently have a lot of sort of future, then we can render closer to the service time because we're sort of guessing that snapshots will be arriving consistently. But if we don't have a lot of future, then we sort of have to render further back. And so if we go to get interpolated, what this does is, so we have our server time, and then we've assessed, okay, well, maybe the snapshots are coming in very reliably and quick, and so our render time can be closer to our server time. And so we look at our history, our snapshot history, and we go, okay, find two snapshots where the render time is between those two snapshots, and then interpolate between them. And then so as we increment our server time, and by extension the render time, over frames, the actual interpolation between those two snapshots will grow, and that means that we can have this sort of smooth, smooth view of other players, even though we're receiving sort of infrequent snapshot updates. So the idea is sort of like when you're playing a network, like multiplayer game, you're not actually seeing the players, as they see themselves. You're seeing them sometime in the past, and that's sort of like a major like theme. So like for example, when you shoot, and that input is sent to the server along with a timestamp, you're not, that sort of actual like hit test isn't occurring against the player as they are, currently at that moment. What happens is we say, okay, well that shot occurred at this particular time frame, at that particular time. Where were the other players at that time? And then the hit test is done against the players as they were at that time, and we can see that in lag compensated shot. So we have the shoot time, and we get the particular frame at that time, and then we do the sort of ray intersection test. And so if you've ever had the experience of like playing CoD, and you sort of you get behind a wall, and you're like, I'm safe, I'm safe, and then all of a sudden you just die, and you're like, well, how did they shoot me? I was behind the wall. Well, it's because the other player did have line of sight, they did shoot, and it just took a bit of time for the actual server to resolve that. And so it can feel quite annoying, but what you get in return is that everything can feel instant, even though you might be playing with someone hundreds of thousands of miles away. So what kind of networking do games actually use? So I think the first thing you learn about networking is that UDP is fire and forget, and TCP is reliable. What you send is sure to arrive and to be processed in the way that you intended it to be. So do you use UDP or TCP for games? We use UDP. Why? Well, consider first how TCP actually makes those guarantees. Ultimately, all networking is packet based. It's just that TCP provides the sort of abstraction that writing to a socket is like writing to a file. If you send a 1 GB file over TCP, it's still split up into packets. There's just a lot of bookkeeping that goes on at both ends to ensure that reliability. So, in every packet that TCP sort of splits a file into, it will have a sequence number, so that the recipient will know how to rearrange them to rebuild it. And then every packet that the recipient receives, it will need to send back an explicit acknowledgement packet, so that the sender knows, okay, the recipient got this, okay, well, it hasn't sent an acknowledgement back for this, I need to resend it. And so that's how TCP guarantees reliability. It's not magic, it's just extra bookkeeping. And considering the needs of the game, right, versus like what TCP is great at, something like sending huge files. Well, we need to send small amounts of data that will always fit within one packet very frequently. And we're in a situation where old data is actually worse than no data. Like if we have a few packets dropped, like a few input packets or a snapshot, it's not that big a deal. We can generally just sort of smooth it out, and the users sort of won't notice. So we don't actually need that reliability, but there are certain things that we do need reliability for. In this case, a player actually, you know, dying is something that every client should acknowledge, should definitely know that it happened. And so, our inputs and our snapshots, they don't need to be reliable, but certain messages do. So do we use TCP for this? Well, no, we don't actually have to. We can take advantage of the fact that we have this frequent bidirectional traffic. We're constantly sending inputs one way and constantly sending snapshots the other way. And so for each sort of packet that we send in each direction, we can prepend a header and have sort of 32-bit bit field that encodes the last 32 messages that were sent between the peers. So like what this essentially means is that instead of having to send an explicit ACK back, if the server sends to a client, this player died, and it wants to know that that client received that message, instead of sending an explicit ACK back, it will just flip a bit on the next input it sends to the server, and then the server will be able to register that as an ACK, right? And so that just saves on actual bandwidth, and we get all the reliability we need, but we don't have to use TCP because we can use this property of our system, which is frequent bidirectional traffic. Something that I want to mention is that this project has no dynamic memory allocations, at least in my code, or at the very start when I'm sort of generating meshes. On a frame by frame basis, there are no dynamic allocations. Now, games in general, but like in particular, network games, should be predictable in the amount of work they have to do on any given frame, and there shouldn't really be a huge amount of variation. What I found when actually building this was that it was quite easy to define an upper bound on the amount of entries I'd need in a collection. So, there are a maximum number of players. There is an upper limit to the amount of shots that need to be processed in a given frame. And when you don't have dynamic allocations, it's easy to feel sort of more secure about how predictable your system will act as a whole. Although dropping a few packets is fine, you do actually want the systems themselves to be working reliably. Now, the last thing to mention is a sort of key data structure in this project, something that makes it sort of work at all, and that's the ring buffer. And what a ring buffer is essentially is it's a queue where pushing onto it, you do a modulo of the capacity of the queue, such that pushing to index 11, you'll take them with a capacity of 10, you'll take the mod and you will then write to index 1. So then it has this sort of wrapping around functionality. Now, consider many places in the code where we want to push entries onto a queue and implicitly invalidate entries older than a certain age. So the inputs that we replay for client-side predictions, or like the snapshots that we interpolate between, on the history, the snapshot histories that we keep for lag compensated shots, these entries are valuable for a certain period of time, and then they're garbage, right? Like where a player was 5 seconds ago is not useful. And what a ring buffer allows us to do is continually just push onto it these entries, and implicitly invalidate older ones, so that we never have to do any work to remove them. So let's see it now with and without client-side prediction. So without, when I move left and right, there is that pause after the camera tilts, that's when the keys are going down, to when I'm actually moving. But how I view myself and how the other player views myself is the same. That's because what is being rendered derives from the snapshots that are coming back from the server. When I turn prediction on, then that's no longer the case. My movement feels instant, but as you can see now, my view of myself and the view other players have myself is no longer sort of the same. So other players view, myself in the past relative to me. Um, and so that's pretty much it. Yeah, that's the project, and thanks for watching.